All right, good day, guys. Today we're going to be talking about critical attributes of similar figures. We are now in the first workbook, Chapter 4, Lesson 2. I am aware that we bounce around back and forth, which is why it's very important that you guys pay attention each day and check online so you know exactly where we're going to be. So, as always, or as typical, I'm going to go ahead and leave out this first page because I want us to discuss that as a class together. Instead, I'm going to go right into page 322 and discuss our examples and our idea. Our big key concept for this page on 322 is the idea of how to identify a similar figure. It tells us, our definition up here, that if two figures have congruent corresponding angles and the ratios of their corresponding sides are equivalent, then they are similar. That's a lot of words to take in, so we're going to go ahead and kind of break this down. Now, first of all, we have the word there that says congruent corresponding angles. Congruent means the same or of equal measure. Corresponding means matching, and angles are these things over here. These are all angles. And you guys are all familiar with this one in this shape, the very common 90-degree angle. Now, if you notice that these two rectangles, although they look alike, are not exactly alike. So they are what we call similar figures, which is by definition what a similar figure or similar figures are. Shapes that look alike but are not exactly alike. But they are mathematically related, and you can prove that, and that is the whole point of today's lesson. What you want to look at, first of all, is look at some of the properties these shapes will have. You know that they will have the same measurement of angles for both shapes. For example, all four angles in this big rectangle match the same four angles in the small rectangle. But the only thing that's different is the actual length of the sides. And there's different ways to go ahead and compare them. Here they give us several examples. They took several sides, for example, the bottom and the bottom over here, and they compared them. We know that 10 and 5 can be, are basically related by the number 2. That means that this rectangle, if you take the sides and multiply it times 2, you get the sides of this bigger rectangle. So this big rectangle, in effect, is twice as large as this one. If you were to compare them backwards, maybe you were to compare the small sides to the big sides, then what you would get are, you would get a 1/2, which means that this rectangle is 1/2 the size of the larger rectangle. But those kind of things will be addressed later on in our examples. Let's go ahead and look at our first example. And right before we get to that, we have a little more information. Figures that have the same shape but not necessarily the same size are called similar figures. There's our definition again. It says the rectangle above HJKL is similar to rectangle MNPQ. This is written as rectangle HJKL and rectangle MNPQ are similar. What you're going to see here is a single little squiggly line. That means similar. Not congruent. That's when you have two little lines, but we're not dealing with that today, or at least not right now. So in our first example, we have two trapezoids. If you notice that these trapezoids, one is bigger than the other. One has the little small end facing to the right, while this one above has it facing to the left. So we have two trapezoids. Both look similar, but we have to prove if they really are. Now, the fact that they both don't face the same direction is irrelevant to us. And there's two ways to prove if two shapes are indeed similar. The first method I'm going to show you here is when you compare just matching or corresponding measurements. For example, I'm going to go ahead and write down the letters or the name of this first trapezoid. Now, what you have to know is that when you have shapes that are named, they are named in alphabetical order. For example, I have the letters J, H, L, and K. If I went in alphabetical order, that would be H, J, K, L. So I'll go ahead and write that down here. Trapezoid H, J, K, L. We want to check, we want to see if it's similar, so I'll put a question mark here, to triangle trapezoid A, B, C, D. Here's one of the properties of shapes you're going to need to know. Whenever you have shapes with letter names, the letters all have to correspond to the matching sides of the other shape if they are indeed similar. Now what I want to do is compare some sides. I see that on the big trapezoid down here, I have this side down here from A to B is 10 kilometers. A to B is the first two letters of my second shape. That means it should match the first two letters of my first shape, which is HJ, from here to here. Now, down here I went from left to right. Up here I went right to left, and that's because the shapes are in reverse positions. They are facing each other in opposite directions. So what I'm going to do is compare side AB from the big trapezoid to side HJ from the small trapezoid. It doesn't matter if you want to go big shape to small shape or small to big. Just make sure that whenever you compare them, you always go the same way. So I'm going to go ahead and compare AB which I know has a side length of 10 kilometers, and side HJ, which has a side length of 4 kilometers. This is a ratio that I can simplify to 5/2 kilometers. And then now I have an improper ratio, which I can make into a mixed number, and I get 2 1/2 kilometers. So that means these two sides, this side and this side, are related by this. That means if the smaller shape is 2.5 times smaller than the big shape, or if I say it backwards, the bigger shape is 2.5 times bigger than the smaller shape. But you need more than one side to prove if two shapes are similar. So I'm going to pick two more sides. Now, unfortunately, I can't pick this small side here or here because they don't have any numbers. So I'm going to pick some other sides. Here I have this long side from A to D. A to D is my first letter to my last letter, A to D. That has to match then the first letter to last letter of my second shape, H to L. H to L is 6 kilometers. So I'm going to go ahead and, like I did above, and fill out my information. H to L I just said was 6 kilometers. A to D is 15 kilometers. I'm going to simplify this ratio by 3, and I get 5 kilometers to 2 kilometers. And just like above, I get the same simplified ratio of 2.5 kilometers. So since I have two sides that have the same equivalent ratios, that proves that these two shapes are indeed similar. And here's the ratio, or here's the amount at which they're similar by. Now, you can also check if two shapes are similar by using a second method, and that's just working within the shape. So I'm going to go ahead and erase what I wrote right now. Oops, I shouldn't have taken that off on top, but that's okay. I'll write it over again. So starting over, we know that, or we think that shape H, J, K, L is similar to A, B, C, D. Now, another way you can check is using the shapes separate from each other. For example, I'm going to take AB from my big trapezoid and compare that to AD from the same trapezoid. I'm going to take those measurements. I know A to B is 10 kilometers, and I know A to D is 15 kilometers. 10 to 15, this ratio can be simplified by 5, and I get 2 to 3 kilometers. That's the ratio within this shape, how they're all related. I want to check if the same ratio is true for my other shape. And I'm going to go ahead and use the same exact sides. Side AB, which is my first two letters here, corresponds to HJ, which is the first two letters on my other shape. And then I used AD, which is my first and last letter. That corresponds to H and L from my second shape. Notice that I'm not going back to the picture so much, and I'm using a lot of just my letters up here. This makes it a lot easier when you're comparing, because this way, no matter what shape my direction's facing, I'm not going to get too confused. So how long is it from H to J? H to J is 4 kilometers. Notice I didn't even care which direction it was going. I knew what letters I wanted. Here I have H to L. H to L is 6 kilometers. This ratio can be simplified by 2, and I get 2 kilometers over 3 kilometers. So even though I use two different shapes, they both gave me the same exact ratio, the same equivalent ratio, as we say. So since they have the same equivalent ratios, I know once again that these are also similar. So your task now is to go ahead and work on the first got it that we have down here, which is got it number A. Use both methods. Not only do you have to determine if they are similar, but you also have to explain how you know. You can either use the first method, where you check equivalent ratios between the two shapes, or you can use the second method, where you take two sides from each shape and see if you get the same ratio. Either way, you need to be able to prove it, and that's going to be part of your assignment when we check it. Moving on to page 323 now. On the top, we're going to use the fact that we know how to prove that two shapes are similar, and we're going to go ahead and check and use that information to check how to find missing sides. Here, there's some new notation you have to see. We already know how to read this right here. Triangle ABC is similar to triangle XYZ. And in this case, we have two shapes that are side by side. This one's obviously smaller than the first one. Their lettering even matches the same order. This is the rare case. Almost every time on any assignment or test, your shapes will be in different orientations. But they put them nice and side by side for us so they can show us how they're even. There are some new marks you have to know how to read. Here we have angle A. Angle A and angle X are congruent, or have the same exact angle measure. And that is shown with this one little angle mark. Here angle B and angle Y are both congruent and have the same angle measure. Same thing with angle C and Z over here. But notice within the triangle, A, B, and C have 1, 2, and 3 marks, which means these 3 angles are all different compared to each other, just like they are over here. They only match the other angles from the other triangle and not any other angles within the shape. Now, we're going to go ahead and skip this part of the symbols because this will become more apparent how the symbols are used and written as we do our next example. Now here, we have 2 similar triangles. I know they're similar because they tell us right here, since triangle ABC is similar to triangle DEF. Now, I'm going to go ahead and just use that bit of information and start setting up my problem. My problem asks us to go ahead and find angle X. It doesn't say it directly, but I know that because it's not labeled that that is what I'm looking for. Also, this whole section that this lesson I'm working on, this example, is about finding missing sides. So what I need to do first is I need to pick any one of my methods. I'm going to go ahead and compare my small triangle to my big triangle. So I'll make a little note, small to big. And I'm going to make all my ratios in that order. Now, I'm going to pick something from the small triangle that I know. I know from A to C that that is 4. So from A to C, that is 4 centimeters. Well then, if A to C is 4, then that means D to F is going to be the matching side, and that length is 12 centimeters. I'm going to go ahead and just take that ratio and simplify it, and I get 1 to 3. This is our scale factor. That means this big triangle is 3 times bigger than this small one, or if I say it backwards, this small triangle is 1/3 smaller than the big triangle. Knowing that, I can now find my missing measurement. I want side X. I need to make a ratio. X matches up with this side over here, which is 6 centimeters long. I know that these 2 things, from the big to the small, have to measure or match up to my ratio. Remember, my ratio was small to big. So I'm going to flip this around. Instead of 1 to 3, I'm going to say 3 to 1. With ratios and scale factors, you can flip them depending on which way you're going. Since X came from my big triangle, then I have to take the side that matches my big triangle, which was going to be the 3. Now I have 3 to 1. I'm going to go ahead and multiply by 6 really quick. One moment, really quick. All right, so my ratio is still correct. This is my scale factor, but just turned upside down. And I'm going to go ahead and just cross multiply. Whoops. Let me take my pen here. I'm going to go ahead and cross multiply. 6 times 3, which is 18, equals, and I know you guys have seen this butterfly cross multiplying before in elementary school, times 1 times X, which is X. So there's my missing side. Another way I can see this is looking for another pattern. I can say 4 times, let me get my pen going again. 4 times 3 is 12. So then 6 times 3 is whatever that missing number is, which is 18. There is more than one way to find the missing side. And that's exactly what you're going to be practicing with this example. In the next